it is meant for the service operation. The vessel which you have prepared as per code, constructed, inspected as per code, now it is in operation. In the operation, if we just think about the local metal loss or a general metal loss, because it's easier to relate. Now, when do we need to do the assessment? Let us say I've done the inspection after 5 years. Okay, the plant was shut down, a routine inspection was done, and you found some corrosion which has happened. In which case do you think I need to do fitness for service? Do you think in all the cases I need to do? Or there will be some cases which will require fitness for service assessment. So in which case we require, tell me that in the chat. So let us share in which case. I hope the question is clear. There is equipment. There was some corrosion allowance which was given. There was some corrosion rate. You have done the inspection after 5 years. In which case I need to perform fitness for service? Is it that for every case I need to do, every time I have to do fitness for service? Or there is a particular case which will induce the API 579 inspection? You have done the inspection. If I have given 3 mm corrosion allowance for 20 years, what is my corrosion rate every year? If I have 3 mm corrosion allowance, which I've allocated for 20 years, what is my corrosion rate? Give me that. 3 by 20. Right? I read few more responses. 3 mm corrosion allowance spread for 20 years. Yes, 0.15 mm per year. Now I have done the inspection after 5 years. Okay. Now what will be my expected corrosion which might have happened? And let me give you the thickness also. Okay. Let us assume that my thickness which I started was 20 mm. Okay. So I've taken 20 mm thickness and nominal thickness. I've started with that. After 5 years, I have done the inspection. What is the minimum thickness which you'll expect after 5 years? So 0.15 into 5, which is 0.75. So that is the loss. That is the loss which you'll expect. So 19.25 is minimum which you are expecting. Okay, based on the calculation which you have done. Okay, all of us understand that corrosion allowance with which you have started, that is just an estimation based on experience, based on similar services conditions. Okay. It's not an exact value, isn't it? Corrosion allowance with which we start the design, it's not a fixed value. It's just an estimation which we have taken. Now it has to be assessed after every inspection. Okay, so I've done the inspection after 5 years, so I'm expecting 19.25 as a thickness, minimum thickness which I'm having. Okay, now what if you got the thickness as 19.1? It may be local or maybe gross some area. You found that the metal loss is a little bit more than 0.75, so it's 0.9 instead of 0.75. Then I need to do fitness for service. Okay, then you'll be assessing, okay, that can my equipment run for certain period, like if my inspection is planned for maybe next 5 years. So with what is the corrosion rate which is currently we are having, and if it goes with the same corrosion rate, okay, whether I can run that equipment for the next 5 years, okay, or I should think of either repairing or replacement. Okay, so if my expected corrosion allowance which I have provided, expected thickness, you can say expected thickness should have been more, but I found that my thickness is less, more corrosion has happened. Okay, in that case, I can perform fitness for service and assess what is the remaining life, and definitely for the next, when we do the assessment, we do for the next shutdown. Okay, is my equipment fit for operation for the till the next maintenance time? So if it is, then you can keep on running. If it is not, you may think of first derating that component, using it for lower pressure, which is called derating. Okay, derating is nothing but using it for lesser pressure or temperature conditions, okay, than the design. Okay. So you can do that, or you can plan for a repair. Okay, maybe you decide that, okay, it is good for 5 years, but then in the next shutdown, I need to do some repair on that. Okay. Or you can decide to replace. Okay. So all these things comes when it is not going in line with your calculation. Yes, Sidhural, you can speak. Go ahead.
So just adding with that,
Yes.
once we get the thickness and we found that we lost some significant wall, but still it's within above the mean, it means that we are losing the wall more faster than expected. It may there is something wrong in the system. So
Correct.
first thing we usually do is to implement an inspection regime that actually reduced frequency.
Yes.
To frequently monitor that one till so that we are safe till next shutdown. We do the corrosion rate remaining life calculation and check that can we reach up to the next shutdown. At the same time, we might need to find out, investigate on the reason for that, because if it is not general everywhere, it is localized,
Yes.
then maybe flow assisted or something. So that location will go for monitoring. If it is general, then we need to check the chemical composition to treat the corrosion actually, because repair or changing the segment of the pipe or equipment, it will not give us sustainable solution.
Yes, again, the same problem will keep on
going on.
Yes. Yes. Thank you, Sadhu. Thank you for adding up a very good point which you have mentioned. So yes, so level 1 assessment is like that only. It's a very small calculation. It's like you can do just on the spot. Okay, and you give you an idea that whether I can run it for the next. You may even decide to increase the frequency, like Sadhu shared, because if it is corrosion is happening with a faster rate, okay, what is the reason for that? Okay, and it should not happen that, see, still you cannot say that further 5 years whether the same rate of corrosion will be maintained or not. Right? If it has happened more in the last 5 years, the rate may be even higher. We never know. If you don't know the reason why it is happening, okay, so you may increase the frequency of the inspection. Okay? You can decide that, okay, let us monitor it more frequently than earlier and see how it is behaving further. Parallelly, you also try to find the reason behind that. Okay, because you'll just eliminating the outcome may not be a sustainable solution, right? If I'm able to find the root cause of it, I can increase the complete system life, okay, and that will be a better solution. So you always try to find out why that happened. Okay, if it has happened very locally, definitely there is some reason for accelerated corrosion at that location. So whatever design conditions we have taken, okay, whether something which is unwanted has happened, and what is the implication of that? If I found a crack, okay, what will be the implication? Can I run it? Can I eliminate? Can I do any repair for the crack? Mostly no. Doing repair of a crack is not possible. Okay. What is the reason for the crack? Okay. Whether I can sustain it for a certain period or not. Okay. So maybe there's a local gouging of a material because something has hit your component. Okay. In the site, it may happen, right? Something externally has damaged your equipment. So what is the implication of that? Okay. Fire damage. Fire has happened in some other equipment, but your component was very closer to that. Then you have to evaluate what is the implication of that fire. Okay. So corrosion, if you have noticed, there is a pitting which has happened. Can I continue? What will be the implication of that? What is the gravity of that pitting? Whether it is a very gross or it is at a very minute level, I can go ahead with that. So all these kind of thing which we combine, and we have created a standard which is fitness for service based on all the experiences which people had. Okay, so learning this gives a very good tool to deal with all these activities. Okay, otherwise you may not be able to decide what exactly you have to do, and even if you decide whether it is acceptable to the inspector or not, that will become a challenge. Okay, so if you have a method, if you have a standard for that which everyone is following, it makes our life very easy. Let us start one assessment and let us try to go into detail of it, and that will give you an idea about the other also. Okay, other assessments, what exactly might be done in that. So that also will be very clear. Okay, so let us start with that. So if you talk about fitness for service definition, okay, so very simple. The name itself is very clear. Fit for continued service. Mainly our concern is to the next shutdown. Okay, so whatever my planned shutdown time is there, till that time, whether I can run it or I need to plan some repair for the next, or maybe you have to do the repair at this stage itself, or replace at this stage, or maybe after in the next shutdown, I have to plan for the replacement. Okay, because if I have to do a replacement of a component or equipment, it cannot be done immediately. I have to plan for that. It is having a certain timeline. So unless I know it beforehand, my plant will wait for that equipment to be manufactured and come to your site. So that is undesirable condition and it will lead to lots of losses. So it is a very, very helpful and very useful tool. And now, see, we are in a situation where most of the plants are more than 20 years of experience. Almost 80 to 90% of the plants worldwide have reached this stage where maybe they are 15 or 20 years of operation. So doing fitness for service has become a mandatory thing, and most of the equipment will ask for that. So the demand for doing this assessment, you'll find it that it is raising day by day. Okay, so we should be aware of these procedures. Now, let us before diving into deep, we discussed lots of other assessment, which is like pitting damage, local metal loss, general metal loss. Let us see what are the different types which we generally see or assess by 579. See, 579 is a relatively very new standard. Okay, and it is still in development phase, and lots of other parts also will be added. It's not a constant thing, and you'll see in the next version, few parts will be added. Okay, and few parts will be you'll be seeing more development, new rules coming. So that is ongoing process. So depending upon the different damage class. So first let us identify or talk about what are the different damages classes. So first one is brittle fracture. What do you mean by brittle fracture? What is brittle fracture? I think if you are a tank designer or even piping, all of us might have heard this term, brittle fracture. So what is brittle fracture and what is the term which is linked with that? When we talk about brittle fracture, what exactly it's a catastrophic failure. Ritesh, yes. MDMT. Okay. So whenever brittle fractures comes to our mind, MDMT is the term which we generally think. Okay, so it is linked with that. What is the minimum design metal temperature of my equipment? Okay, so that will decide whether my complete component will be in work operating in a which zone, whether it is in elastic or it has become a brittle. Okay, so sudden failure is going to happen or not. That is what basically we are trying to assess. Okay, so whether my steel is elastic or it is brittle. So brittle failure is a catastrophic failure, and it does not give us any indication. Okay, and that is the reason it's very, very dangerous. Okay, the second is corrosion erosion. We have already discussed about that. So it is an ongoing process. We always design the component most of the time with corrosion allowance. So if it is in service, corrosion is expected for most of the material and services. So this is a very well-known damage class. Crack-like flaws. Now, crack-like flaws, we never deal with this in a normal design. Okay. Your material in a fresh condition not supposed to have a crack-like flaws, okay, which is not acceptable. See, crack-like flaws will be there in your material. You cannot fully eliminate. Okay, so some cracks, some length, which is acceptable by the code, is permitted. Now that crack may expand due to various reasons in the service. Okay, so if you have found in service inspection there is a crack which is beyond the code limit, so you can do part 9 assessment, which is assessment of crack like flaws. Okay, then you have fire damage, you have creep also. I think most of us will be familiar with. It's a high temperature phenomena, high temperature, high stress. Okay, mechanical damage, some component hit your equipment during service, okay, because of some movement of the trailer or something. So this is also possible. And fatigue. Okay, fatigue is also a widely known phenomena, and I think all of us will be familiar with fatigue also. So it's not like if I have a one type of damage. Most of the time it is mixed. Like if you see if I have a fire damage, definitely have to do a fire damage assessment. But apart from that, it may have created some metal loss. So I may need to assess with part 4 also. It may have created some localized metal loss. So I may have to evaluate the damage with part 5 also. Okay. It may have distorted my shell. Okay, so the shape might have changed because of the heating, external heating. Okay, so of saddle or skirt. So I have to assess for that also. I have to assess for a crack-like flaws if I have observed something. Creep, if my temperature has gone into that zone of the creep zone for the material, I have to assess. So for qualify one class of damage, I may end of doing multiple evaluation. Okay, so it's not like only one type of evaluation for one type of damage. Okay, so like brittle fracture, we definitely will be doing brittle fracture assessment, but brittle fracture may generate cracks. Okay, so crack and brittleness both are linked together. Okay, so crack becomes really, really dangerous if you are very close to brittle zone. Okay, so crack is not a problematic phenomena when it is elastic, when the material is elastic. Okay, it is very problematic if my equipment is near to brittle zone. Okay, so very, very important. Similarly, if I have a corrosion, depending upon the nature of corrosion, whether it is local, okay, so part 5 I'll be doing, or if it's a general, I'll be doing part 4. I may do the combination of both. Okay, if I've done the inspection, some places it was local, some places it was general corrosion which has happened. So I may end up doing both. Then I may found pitting also at some areas. Okay, so I can assess that pitting also. Assessment of blisters. Okay, that happens when we have hydrogen services. Okay, so blistering can happen. Okay, so which is also called HIC. Okay, another type of hydrogen induced cracking. SOHIC. So multiple types of damages may happen in the hydrogen service. So that is also assessed by the separate assessment, which is part 7. So part 7 is not only about blisters, but it is about HIC, SOHIC. Okay, so any damage class when you're assessing, it will be result of multiple most of the time. Okay, so we need to learn each and every part to be able to be qualified as a fitness service engineer. Okay. Now moving to more detail. So the next thing which will come into your mind is part 4 versus part 5. What is general metal loss and what is local metal loss? Okay. So if I ask from you guys, what do you think? What is how you can define or differentiate part 4 and part 5? any way you can, or what are the things which is more conservative, whatever you want to share. Part 4, which is general metal loss, versus part 5, which is local metal loss. Part 4, uniform corrosion. Pitting is a complete different types of corrosion, Saidur. Okay. So uh, it is a local loss, and sometimes pitting may result into doing part 5. Okay. Sometimes pitting may be analyzed as a part 5. It is done because if pitting has happened and the shape is large, you may end up removing that pitting, and finally, if you remove the pitting, it will look like a local metal loss. Okay. So it is done, but normally it is a phenomena which is you will see multiple dents kind of thing on the equipment, and depending upon the image of that corrosion, you'll be able to decide whether I need to go ahead, which is acceptable, or which zone is it is, and what will be the roughly size, diameter of the pitting and depth of a pitting. So depending upon also you can qualify. Okay. The only difference is that pitting will always happen in clusters. Very rarely you'll find it as a one or two pitting has happened. When pitting has happened, it will be a cluster of it. While local metal loss is may happen due to some reason of maybe a flow is having a particular pattern at particular location. So that place you'll find local metal loss. Okay. Great. So part 4 and part 5. So part 5 is a local metal loss. So if very local area, now the definition of local and in general, that is also defined in 579. So there is no confusion in that part, which you will classify as a local and which you will classify as a general metal loss. Okay. Now, if you are analyzing a local as a general, that will not be a conservative assessment. Okay. If you are trying to analyze a local metal loss by applying a general metal loss approach, like analyzing a part 5 kind of damage with part 4, will that also can be done, but will not give you the accurate results. Okay. You may be disqualifying a component which may be otherwise qualified. Okay. So part 4 is very general. Okay. When you are applying part 4, you are considering that uniform thickness, uniform corrosion, or uniform local metal loss has happened everywhere on the surface. It's not local. So you'll not take the credit of the additional thickness. Okay. Now let me explain that in a little bit more detail. So if this is my thickness, which you can see on the screen, let me just hope you're able to see that. So this is my normal thickness. Okay. Now, let us say this is kind of local metal loss which you have found, okay, in the inspection. So when you are doing part 4 assessment, which is thickness averaging approach, it will consider that it will calculate the average thickness, and it will consider that all the thicknesses, okay, in the complete component has corroded. Okay. And it will not take advantage of the thickness which is there in this area. It will not take advantage of that. While when you do the part 5 assessment, it will take the credit of these thicknesses which are in the surrounding area. Okay. So you will be able to qualify a damage, which is in part 4, you cannot qualify, but you can qualify by part 5. Okay. So there is no very hard boundary between these two. There are certain conditions which will be required to be met to be analyzing it as a part 5. But part 5 does the calculation more accurately, while part 4 treats a general assessment rule and very simple approach, very simple calculation, very conservative, okay, but may end up disqualifying some damages which can be qualified by part 5. Does it make sense to all of you? Okay. Sadhu is writing, in case of localized metal loss, ancillary area treated as reinforcement. Yes, that's what we were discussing about. So part 5 takes the advantage of the area where it has not corroded. So surrounding area which is still there, it takes the advantage of that. Okay. While the local metal loss, it will consider completely the thicknesses has gone down, so it does not consider the advantage of the other portion. So that is the reason it is very conservative approach, but may lead to rejection of the defects which otherwise can be qualified. Okay. So applying part 4 for a local metal loss, you may end up rejecting the component. Okay. So if it is local, try to qualify that by localized metal loss. Before we go deeper into the part 4 assessment, we need to understand the component type. Okay. Now the component type means whether my equipment is simple to do the calculation or it's a complicated portion where that defect has happened. Okay. Now to make it even further simpler, whether the defect which you have found, if it is in shell, whether that is simple, or if the defect has happened in the tube sheet, that is simple. Which one do you think? Defect in shell is simple to analyze, or defect in tube sheet is simple to analyze? Which one is simple? Shell is simple to analyze, or descent is simple to analyze? Okay. If the defect has happened in the area which is a discontinued area, a discontinued kind of shape. Okay, it's not a continuous shape. Okay, the example can be the flathead to shell junction. If the defect has happened there, it's very difficult to analyze, isn't it? So same way like shell, we have a very simple equation where the thickness calculation is directly linked with the shape and the material. Okay, so if I have the thickness which I have measured available with me, I can do the calculation very quickly. In the tube sheet, we have some equations, but is it directly linked with thickness? Is the calculation directly linked with the thickness? Like, I can apply that equation and find the thickness. Is it that, or it is a multiple, it is related with thickness, definitely. It depends upon thickness, but the equation is not directly linked. Okay. What you'll be analyzing is stresses. Do you agree with me? So are you able to differentiate between these different types of component? What do we mean by that? Okay. Is that becoming clear to all of you? Shell being a very simple type of component. And definitely this, when I'm talking about simple, okay, it is also a geometrical dimensions which also comes into play, right? If my shell is a part of a column which is very tall, now can I say that calculation of stresses in shell will be very simple? Yes or no? A shell which is a part of a horizontal vessel may be very simple to calculate, or a length is not very high. A vertical vessel where height is h/d ratio is small. Okay. Compared to a shell which is part of a tall vertical column, can I say that the calculation of the stresses or the thickness of the shell will be simple? Come on, participate. What do you think? Thickness calculation for a column versus thickness calculation of a simple air receiver. Okay. Which one is simple? Okay. What is the difference in column? When we are talking about column, what is the difference in calculating the thickness? What is the difference in thickness calculation? Why it is difficult? See, all of us will agree that it is difficult, but why? Why it is difficult to calculate? What is making it difficult? The additional loads. Very good, Akshay. Okay. So additional loads which are coming. Okay. So which is called supplemental load. So supplemental loads like wind, seismic, okay, which will create a bending kind of stresses in the shell. So any load which is apart from the internal pressure. Okay. Dead weight calculation may be simpler in a shell, but in other cases, the dead weight also may be very difficult to analyze. Okay. Related to that, the internal pressure, most of the equipment, we have the calculation directly available for internal pressure, right? But whenever supplemental loads comes into play, like wind, seismic, dead weight, eccentric loading, okay, thermal loading, it makes our life difficult. Okay. So the classification which we are going to study, component type, depends upon both the simplicity of the component, like whether it is cylindrical shape or a tube sheet or a nozzle connection, to a geometrical limitation, what is the ratio? Whether it is part of a column, the h/d is very large, diameter is very large, then also it becomes difficult. Okay. So all these comes into play. And apart from that, the loading also, whether only internal pressure is the loading or supplemental loads are also applicable. So all these phenomena are considered while deciding the component type. Okay. Now let us start with what are the different types. So type A, very simple. The components where design equation directly links with the thickness. Okay. Cylindrical shell. I have a thickness formula which is directly linked with the stress in the vessel, the material, okay, or the loading, pressure. Okay. So design equation directly relates with the thickness. I will be able to immediately calculate the thickness if I'm aware of the internal pressure. Okay. Now, this is not the end of it. Apart from that, if only the internal pressure is the loading, okay, there is no supplemental load, only internal pressure is the loading, then I'll classify that component as a type A. Okay. So you can, if you are noting it down, I'll request you to note it down because I have not covered everything in the slide. So type A component, design equation directly relates with the thickness. Okay. Apart from that, only internal pressure is the design loading. Two things. Then there is a geometrical limitation also. Okay. For type A component, my h/d ratio should be less than 3. Okay, you can write it down. H by D ratio. H is height, D is the diameter. So H by D ratio should be less than 3. Clear? If I'm talking about only diameter, then diameter also should be less than 3 meter. Okay. Bigger than 3 meter, I cannot call it qualify it as a type A. So my calculation is going to be a little bit more difficult. The stress prediction is going to be difficult. So I'll not classify it as a type A. Okay. What else? We've discussed about H by D less than 3, diameter less than 3 meter, and height also, like if it's a column, then height should be less than 30 meter. Yeah. Yeah. So H by D less than 3. You can write down all these conditions. H by D less than 3, height less than 30 meter. Okay. So if it is greater than 30, then it is going to be becoming more and more critical. Similarly, diameter should be less than 3 meter. Okay. If it is a horizontal vessel, then L, which is the length between the two supports, so L by D ratio also should be less than 2.5. Okay, that is another condition for type A component for a horizontal vessel. L by D ratio less than 2.5. Yes, Gaurav, it is given in API 579. Okay, so if you open part 4, it is mentioned. Okay. Let me see if I can show it for you. Okay, so whatever criteria which are mentioning, it is from the code. Okay, so you can see here the definition of the different types. Okay, and also I think there is a very good sketch for giving the geometrical limitation. Okay, you can see here L by D ratio, diameter. Okay, for vertical component, H by D ratio, and the H value. Okay, so all that is covered in code by different figures and images. Okay. So you can read this part in detail. So if I read it from here, the definition of component A, component that has a design equation that specifically relates pressure with thickness. Okay, so pressure related directly with thickness. Okay, so here directly you'll be able to calculate the thickness by using the internal pressure. Okay. Same way you have lots of examples also which type of equipment will fall into that. Then type B class. We'll talk about that also. Okay. Great. So design equation that relates with thickness. Now type B class 1. What is type B class 1? Any example you can give? Or what do you think will be there for type B class 1? What will be the difference? I think if you go by logic also, you'll be able to give me the combined loads. Yes, so you can see here, same as A, there is no difference depending upon the type of component, the height limitation, everything is related to A. But here, you can also have a supplemental load. Okay. So if supplemental loads are there, along with the pressure, then you'll classify that as a type B class 1, little bit more critical than type A. Okay. Same component with supplemental load. Type B class 2, which directly does not have equation relating in pressure with the thickness, but you have some calculation available. It's not like there is no formula. There is a formula available which somehow relates thicknesses and the internal pressure, and you get the stresses. The calculation may not be directly a single formula which is linking both, but you have some equations available. Okay. So you can also see the example like tube sheet. You have the equation, but it is a long equation, and finally the thickness will result into the stresses. Okay. Same way, flanges. No single equation, but multiple equation to calculate the stresses. Nozzle reinforcement. Okay. So it will give you whether it is qualifying or not qualifying based on the area. It will not give you directly the value of the stresses. Okay. So these are the example of type B class 2. So when we go down from type A, type B class 1, type B class 2, we are moving it to more and more difficult. Okay. So same way type C, which is the end part of it. Okay. So the parts where you don't have a thickness available, thickness calculation formulas available. Okay. Like head to shell junction. I don't have an equation for that. Stiffening ring to shell when you are welding, the additional stresses which are getting generated. Okay, we are not aware about that. Lug type support, tank shell bottom plate connections, you don't have the direct equation. You may use finite element analysis to calculate these. Okay, so these are type C, which are like, you can say the calculation will happen by finite element analysis. Okay, you don't have equation available for that. Okay. Now, any example for type B class 1, class 2 we know. Type C also I have discussed. What about any example of type B class 1? Anyone? Where you may have some supplemental load with pressure. Anyone? Simple equation, but some, yeah. So it's like column, okay. So because of window seismic, you have a supplemental load. The configuration is same. It's shell type. It is within the dimensional limit which we just discussed. Okay, same component, but here you are having supplemental load, additional load because of wind or seismic or maybe dead weight. Okay. So that becomes an example of type B class 1. Make sense? Clear till this point? Component type to everyone? Where the roof of the tank fails. A very general question. Where the roof of the tank fails. So it may fail at multiple locations depending upon the type which you're having. First of all, the type also may be multiple. So if you're talking about cone type, then cone type roofs, if you are applying a local load, it may fail because of that. If it is self-supported, even the cone type may be having multiple types. Maybe self-supported, it may be girder and rafter supported, it may be column type. Okay, so all the different types will fail differently. Okay, and if you are just thinking about a frangible kind of tank, then it is expected to fail at the junction where the cone and shell is getting connected. It is expected to fail at that junction. Gonna say equipment with vacuum condition falls under which? Is it type A? No, Gaurav. If you remember, vacuum towel. See, if you have to think about any kind of condition, just think whether my formula, which is available to me, directly links the thickness and pressure. So, can I link the vacuum directly with the pressure? Vacuum directly with the thickness? The answer is no. It links by multiple steps, right? First, we'll be finding L by D ratio, then D by T ratio, then go into the curve, and then find the allowable pressure. Okay, so it does not link directly. Okay, so very clearly, code says that it is internal pressure. Okay, which we know that it is linking the internal pressure is directly linking with the thickness calculation. Does it make sense, Gaurav? So it will not be type A. You can classify it as a class 2. Okay, because it is not calculation is available. You have the method available, but not directly linking with the pressure. Okay, so you can classify it as a type B class 2, do the calculation and see if it is qualified. Okay, great. So moving further, now we can start. We have covered all the basics, and we can start with part 4, assessment of general metal loss. It's a very simple calculation. We'll also take one example and do the calculation. But first, we'll just try to see the theory part of it. First of all, we'll talk about the limitation. Not everything you can analyze by part 4. Okay, you need to have certain limitation. Okay, so we'll talk about what are the limitations. So first, you apply this and then say that okay, I can do the assessment if it is qualifying all these following. Okay, now what is that? First of all, the original design has to be with recognized code and standard. If your original design of that particular equipment was not with a standardized code or standard, then you cannot apply 579. Okay, because the rules are always linked with the original design code. And if your original design code itself is not available, it makes it not possible to analyze that component. Okay, because API 579 does not give a different set of rules. It uses the original code and get the thickness calculation equations from the original code and applies that to the component while doing the assessment. Okay, so if the original code itself is not there, then it becomes a limitation for analyzing. Okay, you cannot proceed further. For general metal loss, it has to be smooth. It should not be very sudden, okay, localized. It has to be a very smooth kind of metal loss. Okay. Yes, it is not applicable to non-code. No, non-code is different. Like you may not have stamped that vessel by using Section 8 Division 1, but the construction code remains Section 8 Division 1. Okay, it does not mean that your vessel was stamped or not. If the construction code is Section 8 Division 1, even though it is not stamped, you can apply. Okay, even the original code becomes obsolete. Okay, now you have the latest version, but you have definitely, if it is construction was done 30 years back, you must have used a code which was 13 years older. Okay, still that is valid. Okay, still that is not a problem. You can. Okay, but while if you're doing some re-rating or doing some repair, you have to follow the same code. Okay, the original code has to be followed for that. Yeah, so even though the more versions are not available, still you can use. So even that code is now no longer in uses. Still, you'll be able to use it if it was in the existence during that period, and you have to analyze by using the same construction code again. So now metal loss has to be smooth. Okay, cyclic service. Okay, if it is in the cyclic service. Okay, okay, we are talking about the limitation for doing the part 4 assessment, okay, by level 1 and level 2. Okay, so the current focus is only level 1, but the limitation applicable for both level 1 and level 2. If I'm applying level 3, I can do even for the cyclic services. So again, level and level 2, if you are doing the assessment, it should not be in the creep zone. Again, creep also, you cannot use level 1 or level 2 assessment. So these are the major limitations which are there by analyzing part 4. Okay. Apart from that, the inspection data, what is the inspection data which you have to take for doing the assessment? Okay, because fitness for service starts with the inspection data. inspection data is the backbone of your fitness for service. Everything depends upon the inspection data. Okay. So what data will be required, how the data should be captured, that is also very, very important. Okay. So now for doing the inspection data in point method training, so now there are two methods which are there. One is point thickness. So when we say point thickness, if you have a general metal loss in this complete area, which you can see, so the measurement will be done by random points which are fairly apart, okay, and considering some points at the periphery also, okay, very close to the periphery, and covering complete. Don't take too many points on the other area. Okay, once you have marked that general metal loss area, try to confine your readings within that. Some points may be at the boundary layer. Okay, now the next question will be how many points at least I need to take. Okay, so 579 mentions at least 15 points are required. Okay. Minimum you have to take 15 points. You can take much more than that. There is no limitation on the upper side of more the readings. It is good for that inspection. Okay, so more data, more accurate result in fitness for service, because everything depends upon that. Okay. Now, the other method of taking the data is thickness grid. Okay, so there is limitation on the point reading. We'll talk about that further, like when it is applicable and when you have to move to the next thickness grid. So thickness grid means you'll be making a proper grid of the points. It will not be random. You'll be taking horizontal when we say circumferential and longitudinal direction planes, you'll be taking and measuring the thickness at all the grid points. Okay. So you can see here M1, M2, M3 are the longitudinal planes and C1, C2, C3 are circumferential planes. Okay. Now the data should capture the dimension at the boundary. Okay. Like, this is the profile. So it should try to cover the outer portion. Okay. At least one point should be at the good thickness. So wherever the thickness, the local metal loss has not happened, that is called the good thickness. There also some corrosion might have happened, but it is not more than the actual expected. Okay. It is within the limits. That is called good thickness. So you need to have a boundary at least one point outside. So all these outer boundary will have a good thickness. Okay. And remaining will be having some places maybe lower. Okay. So this is called critical thickness profile. So why it is called thickness profile? Because we draw a profile by using this. Okay. So if I try to draw a profile, okay, by moving at this, so you'll be starting with M3 C1 point, go next, and next point will be the lowest among all these lines. So here, if the M3 C2 is the lowest, then that will be considered in the profile. Next, you'll take which is lowered. Okay. So if it is lower at this point, then that will be considered. So like that, you'll be moving and you'll be getting this profile. This is called critical thickness profile. When you're trying to draw it, you need to have at least 5 points in each direction, longitudinal or circumferential, at least 5 points. You can always take more than that, but you need to have at least 5 points in each and every inspection plane. Okay, that is the requirement. And this local metal loss should be away from discontinuity. We'll talk about that clause also, that what is the minimum distance, because if it is closer to a discontinuity, then the stress pattern we cannot capture by a simple equation, right? So it has to be away from a discontinuity portion so that we can predict the stresses accurately by a normal equation. Because for level 1, for type A and type B class 1, we're going to use a very simple equation. Okay. My metal loss is less than, do I need to do anything? Do I need to even perform fitness for service if my metal loss is less than the specified? Okay. The corrosion rate is less than the specified. The corrosion has not happened with the expected rate, but it is lower. Do I need to do anything in this case? Do I need to do anything if my metal loss is less than specified corrosion lines? The answer is no. You don't have to do anything. That is what is desired. Your metal loss should be less than specified. You don't need to do any assessment. No fitness for service is required. Now, you may have the other case where it's otherwise, the metal loss is more than the specified corrosion lines. In that case, you have to take the data and analyze it by fitness for service. Level 1, you will start. So, I'll also talk about the different levels of assessment. So when we do fitness for service, there are 3 levels of assessment: level 1, level 2, and level 3. Okay. When we talk about level 3, How we do level 3 assessment? Any guesses? How we do level 3? So definitely the criticality increases from level 1, level 2 to level 3. So if you talk about level 3, and if you remember the type of classes for the component, type A, type B, type C. So type C, where no equations are available, that is classified as level 3. So that means level 3 is the critical most. There is no equations available. Then also you can apply FEA. Okay, because for FEA, you don't need any equation. You can analyze the equipment as it is based on the shape. Okay, so level 3 is the critical most. Okay, others are level 1 and level 2, which is based on the calculation. Okay, designed by rule. Okay, so mainly when we do fitness for service assessment and the courses, mainly we focus on level 1 and level 2, because level 3, once FEA comes into play, it becomes a completely different domain. Okay, then there you need to have understanding of the software. You need to understand the design, how to do the modeling in the software, how to do the meshing. Okay, so complete domain shifts. Okay, from level 3. So level 1 and level 2 we can do very easily by either using softwares or using Excel sheet. When most of the cases software is not required, a very simple Excel sheet can give you a very good calculation. Okay, so we will be starting our live session for 579, which is covering the complete detail. We'll talk about that at the end of it. So there will be creating an Excel sheet together and using it for the calculations. That is the major part of this live training program which will be coming. So you'll be having an Excel sheet to perform majority of the level 1 and level 2 assessment. Okay, so if you talk about level 1 assessment, what exactly we might be doing? So the logic is very simple. Okay. Thank you, Saidur. Okay. So thickness reading. First, we'll start with that. I need to have a proper thickness reading available with me. So either I can go, if I'm doing level 1 assessment, I can collect point data also. Okay, just random points all around, covering complete metal loss area, minimum 15 points. Okay, and I'll take that data. I'll find what is the minimum among all that points. Okay, I'll create an Excel sheet and I'll be able to find the minimum thickness among all the readings. Okay, then second, I'll be calculating average thickness among all the readings. So minimum thickness and average thickness. So the next job will be to check whether my T minimum is greater or equal to 0.9 times of average. Okay. Now, what does it mean? Can you elaborate? Like, this is a mathematical language. So can you help me to understand what exactly we are checking it here? Can anyone try to elaborate? What we have collected the data, we found the minimum thickness. We also found the average thickness among all the points. And then we are comparing the minimum thickness with the 0.9 times of the average thickness. What exactly we are trying to do? Okay, let me ask another question, and that may help you to or give a hint towards answering that. If my starting thickness was 20 mm, I calculated the average thickness, not calculated, but measured the average thickness, and I got 19 mm. But one place, the T mm was 15. One or two places maybe, okay, or maybe very few points had, which were very close, were having 15 mm thickness. What does it indicate?
Localized wall loss, and
Yes.
do we actually need a assessment or not?
Correct. So localized nature. Okay, so by using this criteria, we are thinking whether analyzing by part 4 is a good idea or not. Yeah, Prakash is also correct. We want to ensure that should not be a localized corrosion. Okay, but T minimum is very less than 90% of the average. That means this analyzing by general metal loss is not a good idea. We should try to see if there is a localized metal loss. Have another area marcation and try to see or analyze by the part 5 also. Okay, so that is what it indicates. That is a very good hard boundary for part 4 and part 5. So if it is not able to meet this criteria, means I'll directly jump to part 5. I'll not go further and try to analyze by part 4. It's not a general metal loss now. It is becoming a local metal loss if it is not meeting that criteria. Okay, great. So now once this criteria is qualified, like my TMM is more than 0.9 times of the average thickness, that means it is a general metal loss. I'll try to calculate the minimum thickness by using pressure. Okay, so for cylindrical shell, it is a very simple calculation which we use. PR divided by SE minus 0.6P if I'm following section 8 division 1. Gaurav is saying, can you repeat? Yes, I can repeat, Gaurav. So see, we have measured two different types of thicknesses. One is the average thickness which I have calculated. Okay, first I have taken the thickness reading, so that random thickness points I have taken, and I have calculated what is the minimum. I can do that, right? By looking at the values, I can find what is the minimum of all the thicknesses. And then the second, average. How to find average? If I've taken, let us say, 50 readings, I have 50 points, some values, okay, around 19, My original thickness was 20 mm, so I'm getting something around 19, some more, some less. Okay, and there are 50 points. How to find the average? Anyone? Minimum thickness, I think everybody will be clear. We can look at the values, find the minimum among all of them. Okay, so that is the TMM. What about TAM, which is average? How to find? What equation you can use?
Add all and divide by the number of readings.
Okay. Yes, as simple as that. Yeah. So add all the thicknesses. Okay, and then divide by the number of readings. Very simple. Okay. We are using very simple calculation for the level 1 assessment. Everywhere you'll find very simple calculation. Okay, very easy to follow, nothing difficult, but it becomes a really great tool. Okay, if it's easy does not mean that it is not useful. Sometimes we relate easy with non-useful things, but easy but very powerful. Okay, so TM, nothing but average among all the thicknesses, and then you try to check the condition. So 90% of the average. Okay, let us see, I calculated the average of all the points and I got 19 mm as the average. So what will be 0.9 times of 19? Give me that. 17.1. Okay. Now, let us say I got a TMM, minimum thickness among all the readings which I have taken was 17.4. Now, in the current scenario, whether it is greater or equal, is the condition true or false? In current situation, when I got minimum thickness as 17.4 and average as 17.9 times of average as 17.1 mm. True, right? So that means it gives an indication that it is a general metal loss. Okay, if I got a TMM as 15, definitely the criteria of less equal to is not met, and it is also giving an indication that my metal loss may not be local. My metal loss may not be local. It may be may be local. Okay, sorry. So may not be general, but my metal loss may be a local metal loss, isn't it? Because my minimum thickness is going, some points are having very low thickness compared to the average. Does it make sense? Gaurav, and to others also, does it make sense? Okay, that if some point which is completely lesser than the average, that means somehow it is indicating that the procedure which I'm using, if I'm doing general metal loss, I'm trying to say that all the loss of my material is very uniform. So if it is a uniform thickness, will that happen? That some points are very low in thickness. Will that happen? The answer is no. Okay. More or less, all of them will be at similar levels. Okay. The variation in points will not be very high. If it is very high, it is indicating a local metal loss. Okay. Hope it makes sense. Gaurav, this was your question, so I hope it makes sense. Yeah. Great. So if it is meeting the criteria, that means it is a classification is correct. It is a general metal loss. And now you'll decide whether the TC minimum, C indicates the circumferential. Okay, because if I'm calculating a shell, the circumferential stress is going to govern. So TC minimum, by using the pressure, I'll determine. So I'll know that what is that thickness for me, which will be able to take care of the pressure. Okay. Now what I'll do. Okay. Now this TC minimum, when we calculate directly by using PR divided by SC minus 0.6 P without adding any corrosion lance, that is the TC minimum. Okay. So T average, which I have calculated by just averaging all the readings, I'll subtract the future corrosion allowance. Now this is a very interesting term. It is coming for the very first time. So let us, before we go into detail of this calculation, what exactly is future corrosion allowance? Anyone can explain me? What was given to us earlier was corrosion allowance. Okay, and that is the term which we are familiar with. Now, what about future corrosion allowance? And there is also a term ML which is linked to that. Okay. So first let's talk about future corrosion allowance, and then we'll differentiate between FCA, if I'm writing FCA, and if I'm writing FCA ML. What is the difference? We'll talk about that. But first, FCA. What do you mean by future corrosion allowance? Estimated corrosion allowance in the future. Okay. Now, there can be two cases. Okay. First, just think about your good thickness. Okay. In the good thickness, the corrosion allowance or the corrosion rate is more than expected or less than expected. The thickness which we are measuring, I discussed about that. We have a good thickness. If this is my thickness, okay, and there is a local or maybe a general metal loss for a longer period, longer area, the thickness which is at this location, okay, at these points, okay, and these points, these are called good thickness. So good thickness means what you expect corrosion rate to be higher or lower than the expected corrosion rate. The corrosion rate will be lower or higher. Lower, right? That is why we are calling it as good thickness. Right? It is good to go. We don't have to do anything. Okay, maybe equal also. Yes, that is also. So lower, or it can be equal to the rate which we estimated in the start. Okay. The local metal loss or a general metal loss is having little bit higher corrosion rate. Okay. So you may have two different corrosion rate, which now you know. Okay. After doing the inspection after 5 years. Okay. You know what has happened in the last 5 years. What is the corrosion rate at the good thickness? What is the corrosion rate at the local or general metal loss location? Is it clear? Is it making sense, guys? After doing the inspection in the 5 years, when we are doing the inspection, when we read the data, do we have the idea what has happened in the last 5 years? Do we have the rate? Can we calculate the rate at both good thickness and the local or general metal loss location? Yes or no? We can simply subtract the thicknesses and divide that with the number of years. That is the rate, isn't it? Okay. If let us see now, my thickness at good location is 19 mm, and at the location of general metal loss is 18. Can you give me the rate of corrosion at both these points? Corrosion rate means corrosion 20 mm is what I started with. 19 mm is the good thickness which I'm having after 5 years. 18 mm I'm having at low general metal loss location, the minimum thickness. So can you give me the corrosion rate per year in the chat? 0.4 mm. So give me for both good and at the general metal loss location. So good thickness location, what is the corrosion rate? So 0.1, not 0.1, 1 divided by 5. Okay, which is 0.2 mm per year. And at the general metal loss, 2 mm divided by 5. So 0.4. To prevent that corrosion, okay, like Sadhu discussed, externally it is very easy to prevent. Right? Externally, it might have happened because of the loss of my coating or the paint. Okay, so if I'm able to remove and do the painting properly and keep on monitoring that painting, that it is not damaged because of some reason. So I'm making sure that the corrosion rate is now limited. It is not going to be the same in the future. Does it make sense? So now it is prevented. You have taken the preventive action. Okay, like internal case we discussed, there was no internal device which was preventing the flow from going directly to the surface of the metal where that local metal loss happened. Now, if you are able to fit a device which is distributing the flow, you can say that I have prevented. Okay, so if you have taken the preventing measure, you can definitely, if it is external, you can completely eliminate. If it is internal, you may go ahead with the same rate as good thickness. Okay. So hope it is clear till this point to everyone. Hope it makes sense to everyone. So if my TAM, which is average thickness minus future corrosion allowance, is greater than the thickness which is required by the pressure, okay, it is good to go, right? So if this criteria is met, my level 1 assessment has passed. It is qualified. Okay. Is that assessment over, or I need to do something further? Maybe for next 5 years, if that is my assessment period, it has passed. If I'm interested to finding the remaining life of my component, if the corrosion rate maintains, whatever I'm considering right now as a future corrosion allowance, if that is maintained, what will be the remaining life of my component? Okay. If I'm interested in finding that, it is not simple for all the cases, okay, but it is very simple for corrosion type of assessment to finding the remaining life. So even if I don't tell you anything, I think you'll be able to find out what exactly how you will find the remaining life. Can you give me that before knowing the equation? If you have to find the remaining life for the component which we discussed just now, what will be the equation which you can follow? You have the corrosion rate, you have the average thickness, and you have the minimum thickness required. Can you use these three terms to find the remaining life? Average thickness, minimum thickness required for pressure, and the rate. So absolutely right. So what is my average thickness right now, and what is my thickness required by pressure? So this much additional thickness I'm having, right? Which can be used as a corrosion. Very simple. This is available thickness for corrosion. TAM, which is average thickness minus minimum thickness, and divide that with the rate, how much it is corroding every year. So you'll be able to find the remaining life. isn't it? Okay. T minimum is definitely minimum of these two values. So obviously TC thickness in the circumferential will be the governing thickness, because that is the thickness which is governs the stress value. Okay. Now the second also may be useful when you have a supplemental load. Okay. So TL minimum also may govern if you have a supplemental load. Okay. So minimum of these two is defined as T minimum. Now, are you ready to see one example? Quickly see one example, and we will be doing some calculation together. So if you have any doubts about whatever we have discussed, it will simplify for. Now let us read the example. Let's see the condition for the assessment. So internal corrosion on the cylindrical shell of a horizontal vessel with two saddle support has been found during an inspection. Okay, there is an internal corrosion which has been found during the inspection. The corroded area is located between the two saddle supports. Okay, so location of the metal loss is very, very important. PDF means I've shared one sheet with all of you, Ritesh. If you don't have that, I'll share it again. I've shared in the chat. Okay, you can see the chat means in the Zoom chat, you'll be able to find the PDF. Please download if you have not downloaded till now, so that you can let's write whatever you want in that PDF. Okay. So yeah, so internal corrosion has been found. Okay, and then corroded area is located between the two saddle support. Okay. Details regarding the vessel and inspection data is also given. The vessel was constructed with Division 1, 2007 standards. Okay, so for you remember the limitation. So it is with well-recognized code and standard. So we can go ahead with the assessment. Determine if the vessel is suitable for continued operation. Also calculate the remaining life. Okay, if the future corrosion rate is given here as a 0.1 mm per year. If this is the future corrosion rate, what is the remaining life? Okay, what is the data which is available for us? It's a 516 grade 60 material, 2007 edition. Design pressure is 4.5. Design temperature is 200 degrees Celsius. Inside diameter is 484, very small vessel. Looks like to be a pipe kind of thing. Nominal thickness, 16 mm. Shell future corrosion allowance is also given. 2.5 mm is the future corrosion allowance for the shell. Joint efficiency is 1, which was taken during the construction of that vessel. Saddle support distance is given. You know that this data is required to qualify whether it is type A or type B class 1, right? So support distance 1100. Future corrosion rate, which was we saw here also 0.1 mm per year. Okay, so total future corrosion allowance and corrosion rate both are available with us. Now this is the vessel, and around this location that general metal loss was found. So you can see multiple data points which have been taken. It is not very uniform in the image, but when you are taking, try to take it very uniformly, covering all the areas. Okay. Now we have taken at least 15 points that is required. So 15 points has been taken. You can take much more than that. Okay. Now, Sadur is saying if we have 2.5 mm as a future corrosion allowance, do we actually need FS? Yes, we'll see that, Sadur. Okay. So let us see the calculation, and then we can discuss more about that. Okay. So location 1, see future corrosion allowance individually does not govern. Okay. If what is my corrosion rate, that will make it clear if we can go ahead or not. Okay. So we don't know whether we started with 3 mm or we started with 5 mm. Okay. And it is 2.5 in just 5 years. So we never know that. So location, multiple locations we have. Then we have the thicknesses reading at each and every location. So we have 13, 12, 11. Now if we try to see what is the minimum thickness, can you give me that? I'll just make it a little bit smaller. Yeah. Now all the 15 points are visible. So we can say that the minimum among these is 11 mm. Okay. 11 mm is the minimum, and mostly the maximum we have is 13 right now. Okay. Great. Now, the first I'll be starting with the component type classification, whether it is meeting the criteria of type A or type B class 1. So saddle support is 1100, which was given. Inside diameter is 484. So first criteria, the saddle support divided by diameter should be less equal to 2.5. That was the criteria. So I'll do the calculation and say, okay, it has passed. So first criteria is passing. Second criteria, diameter should be less than 3 meters. So that is well within the 3 meter range. That is also passing. Other, is the thickness formula available? So the shell and code is section 8 division 1. So yes, thickness formula is available. Is the pressure, which is internal pressure, is governing the thickness? The answer is yes. Okay. So in current case, we are not talking about the stresses coming because of the saddle support location. We're not talking about the jig analysis, okay, which also will be having additional stresses. Okay. So in this case, pressure governs the thickness. So answer is yes. Okay. So then we can say that type A component criteria satisfied. Yes, it is a type A component. So if type A, that means I can perform level 1 assessment. Okay. So if it is type C, I cannot perform level 1 assessment. I have to directly go to level 3. So that is the reason we have to first classify whether it is type A or what, type B class 1 or type B class 2. So let us start with type uh, level 1 assessment for a type A component. Use the 5 point thickness rating, which is given in the table, and we can determine the TMM, right? We can directly do that in Excel sheet. If you have taken all the point, I will just say minimum of all these numbers. If I have a grid point with multiple numbers, I don't have to look at it and decide. I'll just say TMM. Okay, minimum of all the thicknesses, and I'll be able to get. Okay, same way, if I have to take average also, okay, I can take the average also among all the ratings. Okay, or the average of all the numbers. So if you are putting the data in Excel sheet, it makes our life easier. Okay, so same thing has been done here. Okay, so first taking the minimum thickness, which is 11, and then the average. Okay, the next thing will come. What is the next thing? Once I have the T minimum and the average, give me quickly. What is the next step? Once I have minimum and the average, whether it is localized or general metal loss. So I'll be checking 0.9 times of average. So whether my minimum thickness is greater or less. So now here TMM, this is the condition which I want to check. So TMM is 11. Now what is my 0.9 times of average? I'll just multiply the 12.067 with 0.9. So it is coming at 10.8. So it is passing the criteria. So that means the classification of this metal loss as a general is perfectly fine. Okay. Now I'll calculate the minimum thickness required for the pressure. Okay, it's type A component, so directly I have the equation available, which is linked with pressure. So I'll put all the data. Now, if I tell you to calculate, can you give me, you have all the data which is available in the PDF also. So can you quickly give me the TC minimum? You will require is allowable. Okay, now 2007 edition, if allowable is not available, you can consider the latest also. Let me see what I have taken. You can take the same. So allowable you can take as 118 MPa to make your life easier because you'll need that. So take allowable as 118 so that everybody is at the same page. So everything is available. Efficiency is 1, that is given. Pressure is available. What is the pressure value? It's 4.5 MPa. High pressure. So we have pressure available. Radius. I think we have the diameter which is given. Inside diameter is 484. Okay. So what will be the radius value? Okay, you can consider. Now this stage, there may be one confusion which may come that inside diameter is 484. But what was the original corrosion allowance? Okay, that also will be required apart from the future. Okay, because then that will give you clarity for calculating the thickness. Okay, in this case, if I started with nominal thickness of 16, okay, and finally I'm getting 13 mm as a good thickness, so that is giving you an indication that 3 mm has already corroded. Okay, so if I have to find out the TC minimum, I need the complete corrosion allowance, okay, which can be, so that will be a challenging thing for you. Let me see how many of you are able to get that. What will be the corrosion allowance to be considering? Do the calculation and give me the value. So calculating R is a little bit tricky. Let me see how many of you are able to. So 9.56 is what Ritesh has told. But first, I'd like you to give me the R value. What radius you'll take? That is a tricky thing. Once you're able to get radius, I know that you'll be able to calculate thickness. But to get the radius for calculating TC minimum, that is the 245 is what Ritesh is saying. Okay. What about others? But you don't have to consider 3 mm. Don't consider 3 mm as a corrosion allowance. The data, you have to calculate based on the data which is available. So you don't have direct 3 mm given as a corrosion allowance. You have nominal thickness. 3 mm has already corroded. So definitely the corrosion allowance might have been more. So right now you have the information, which is nominal thickness, the thickness with which you started. You have a good thickness, which is 13 mm. So that will give you the metal loss, which has happened till now. And you also have a future corrosion allowance. You have to use all these values and get the radius. So T nominal minus T average. Is it clear now? So instead of good thickness, you'll be subtracting the average thickness. Okay. So metal loss will be calculated by nominal minus average. T nominal minus T average, and then you add the future corrosion allowance, which is 2.5 mm. So your radius will be 248.43 in current case, and then you calculate the TC minimum, okay, which is now using the same equation. So you can also do that. So try to do the calculation if you're able to find the thickness. Now you have the radius. Radius, please take 248.43. Okay. And S value 118. Efficiency as 1. Okay. And the pressure is 4.5 mm. Everybody is calculating and definitely be able to calculate. So 9.69 is the value which you should be getting. Okay, that is the correct value. Now TAM, which is the average thickness minus future corrosion allowance, will come as 9.567. Okay, TC minimum is 9.69. Is that acceptable? Is that level 1 assessment qualified? It is passed or failed? If my TM, which is average thickness minus future corrosion allowance, is lesser than the TC minimum thickness required for pressure in the end of life, okay, before taking the inspection, next shutdown, or maybe the inspection schedule. So passed or failed? Definitely it has failed. Okay, thickness is lower than the TC minimum. So now you can also do alternative calculation by calculating the MWP. Same equation. Instead of calculating the thickness, we can calculate the pressure also. Not required all the time. Any one of it you can do. Okay. Now, if level 1 assessment is not getting qualified, what will do next? Will I provide the judgment that it is rejected? Do the repair? What will be my judgment or anything else? What should I do now? What I should do now? Find out the pressure that is safe to operate. Okay. But before doing that, I'll try to do the level 2 assessment. Okay. So first I'll try to consume all the level of assessment and then try to derate. Okay. So my next obvious step will be to calculate the or do the level 2 assessment. Okay. Now I've not spoken about level 2 assessment, but let me very briefly touch upon. It's very simple level 2 assessment also. Okay. Now let me just show you how we do the level 2 assessment. I'll show you directly from the code. Then we'll be able to do the assessment. Okay. So this is my level 2 assessment. Okay. This is again applicable for evaluating type A and type B class 1 component, okay, which are subjected to internal pressure. Now here even external pressure supplemental load also can be used, okay, because now we are in level 2 assessment. Okay. So acceptance criteria, directly we can go to table 4.4 and here you'll see the acceptance criteria or the calculation methodology for level 2 assessment. Okay. Level 1 assessment, this is what we did. Average thickness minus future corrosion allowance, comparing it with the minimum thickness. Here, you'll see the same thing because now if you ignore the supplemental load, so ignore the TL, so only TC is there. So TM, TAM minus future corrosion allowance greater or equal to TC. Is there any difference between level 1 and level 2? Is there any difference in the assessment of level 1 and level 2? If the equation looks finally same, ignoring the TL minimum, look at the formulas carefully. How you'll be calculating TC minimum here? See, in the level 1 assessment, your TC is calculated. The thickness is calculated based on the design pressure. While here, your thickness is calculated by multiplying with the RSFA. What is RSF? Remaining strength factor, okay, which is allowable. Now, remaining strength factor allowable for all the codes where it is not mentioned very specifically, it is considered as what is the value of RSFA for all the codes, including Section 8 Division 1, where it is not provided very specifically. What is the RSFA value? Prakash is saying 1. What about others? In Division 2, it is specified, but Division 1, it is not specified. So for all the codes where it is not specified, 579 gives it a value. And what is that value? It's 0.9. The value is 0.9 times P. Yes, Sadhu is absolutely right. So RSFA value is 0.9. Okay. So 90%. Okay. Whenever you are calculating RSF, so mini assessment, you'll be calculating remaining strength factor and then comparing with the allowable remaining strength factor. Okay. So allowable remaining strength factor for division 1 will always remain 0.9. Okay. So pressure into RSFA, so my pressure will directly reduce by the 0.9 factor. Can you calculate the thickness requirement now by multiplying the pressure with 0.9 in the previous example? First, give me the pressure and then give me the thickness TC minimum value by using this pressure. Yeah, NGS 3788 follows the same process. So give me the value of thickness by using, yeah, so pressure will go down to 4.05. Now give me the thickness TC minimum for this pressure. So 8.72 is what Ritesh is getting. What about others? Diameter will remain same diameter. Nothing, no other value will change. Only the pressure will change. Diameter is same. End of life diameter will not change. Royal is getting 8.76. Okay, no problem, Sadur. So data, if you want, I can share it again. So we have the pressure value as 4.5. So multiply with 0.9. Okay, and then the radius value is 248.43. Allowable is 118. We learned something about API 579 today. Now, if you want to become an expert, go deeper into that, then what is the way ahead? Okay, so the way ahead is that we will be starting a live session like what we are doing right now, which will be done every Friday at 8:30 p.m. Indian Standard Time. So you can calculate based on your location. So 8:30 p.m. every Friday it will happen, and it will be live like what we are doing right now. What will be covering starting from part 1 to part 14. All the different classes of damage assessment will be covering. We will be creating an Excel sheet. Already have an Excel sheet which we will be putting the data and doing the calculation, and that Excel sheet will be available to you. Okay. So today I only shared the PDF, but in actual sessions you'll be getting all the Excel sheet for the calculation. Okay. So it includes almost all the level 1. Level 1, everything is there. Level 2, most of the damage assessments are there. I think only 1 or 2 is not there. Okay. Other than that, everything is taken care. Level 3 is not there in this because level 3 needs a different kind of expertise. So we are not covering level 3 here because that will require existing knowledge of finite element analysis. Okay. So it will be live session. Roughly, it will go 24 to 30 hours. Okay, total. And you'll also have 8:30 p.m., not AM. Okay, 8:30 p.m. So evening time, India, 8:30 is 4 a.m. Okay, for Sadur. So what is the location for you, Sadur? Which location you are? Australia? So for some of you, the timing may be difficult. Okay, New Zealand. Okay. So the recordings also will be available. So if for some reason you're not able to attend the live session or not able to interact, so always preferable if you can come, but live sessions, try to attend it completely in live. For some reason, if you're missing out, then you can always watch the recordings, and we'll be doing lots of taste. The study material will be there. Okay. And most importantly, the Excel sheet for each and every part, which will we can use it for all the calculations which you can perform on fitness for service. Okay. Yeah, so community also will be there. Like you'll be part of a community where you can discuss. Lots of fitness for service people are there, and you can ask your questions, answer the others' questions. So good community for everyone. Starting 9th Jan, okay, and 9th Jan will be we'll be doing the first class. Okay, and now first of all, whether it is worth for all of us to do it. So some data, so like I shared, majority of gas plants and global oil and gas plants are more than 25 years of age. Okay, and if you think about 15 years of age, then 80% will be around that. Okay. So, and it is official ASME report 2022. So now all the older plants will require assessment. Okay, so now it has become mandatory for like DNV GL study. It says that or even OSHA and PSM, okay, which are saying that all the plants of which are considered to be a high risk, okay, and they are containing high risk equipments. Whenever you're doing the inspection, perform fitness for service. Okay, and you have to comply with the fitness for service. So lots of jobs you'll be seeing in the near future, or you might be already seeing in your company. So companies are creating a different department for doing fitness for service. Okay, so 50,000 plus FS assessment is estimated. Okay, this is the exact value. Okay, of 2022. Now it is much higher. In future, it is going to be further. Okay. So job posting and everything is there. So this is a skill which is very much required right now for a static equipment design engineer or even an inspector. How to apply? I'll share one simple form. You fill that. Okay. We'll also have a discussion. We'll see whether this is suitable for you, for your career or not. So try to give all the details which we are asking in this form, so that I don't want someone whom it may not be useful to take this. So we'll try to see the profile also. And if it is suitable, definitely we'll give you the opportunity to participate in the live session. So I'll just post the link in the chat. So you have the link in the chat. If you're interested or maybe thinking, you can fill the form and we'll share the further details with you. If anything is required, you can have a separate discussion with us, okay, related to this course. And if you think it is good to go, definitely you can enroll in that.